Hello, thank you for viewing my presentation. My name is Matthew, and I'm doing my CSE545 final project on the open shop scheduling problem, and I am applying a genetics and wisdom of crowds hybrid algorithm to solve it. All right, so the open shop scheduling problem is a problem that consists of n jobs. Each of the n jobs has m operations, and each operation has a different operation runtime. So each job must be completed on a unique machine, and there are m machines. So the constraints for the open shop scheduling problem, a machine can only work on one job at a time, and two machines cannot be working on an operation from the same job simultaneously. And in open shop scheduling, we do not allow an operation to be paused and resumed at a later time. The make span is going to be our metric to define the quality of a schedule. And a schedule, of course, is going to be a solution to the open shop scheduling problem. So the objective of open shop scheduling is to schedule a job operation on machines to minimize the overall make span of the shop. So here is an example of a problem. So optimize a schedule for 5 jobs across 4 machines to minimize make span. Each job involves a series of operations needing specific machines and times. Operations can be processed in any order without interruption on a single machine at a time. And so we have the 4 operations on job 0 and their runtimes, and we have basically 5 of these jobs that need to be evaluated to make a schedule that minimizes make span. Right, here is an example solution to the problem that we just viewed. And what you see right here is a Gantt chart. And so each block on the Gantt chart represents a job, and it's the job's runtime. And so if you notice, the make span is 1146, and machine 3 takes the longest to complete all of its job. And so machine 3 is what's contributing to the make span here. And so if we focus on machine 3's schedule, we notice that there is a gap between job 3 and job 1. And this is because after job 3 completes, the next job is job 1. However, machine 0 is running job 1 at that time. And so machine 3 has to wait for machine 0 to complete job 1 in order for it to move on to its next job in its individual machine schedule. And so that gap right there is sort of what we look to eliminate when we're trying to fill optimal solutions to open shop scheduling. And so take a notice that in our second solution, we reduced the make span from I think 1146 down to 1121. And there's no gap on machine 3 either. And one thing that I wanted to point out is that these 2 schedules for the same job, they actually have 2 near optimal make spans. Well, 1121 is the optimal solution for the make span for the schedule, but the one at 1146 was probably the second closest, but the actual schedules themselves look very different as far as the sequence of machines for each job or each job sequence for each machine. They're different, and so this presents a challenge in open shop scheduling. Also wanted to point out a second example here where we have 5 jobs and 5 machines. So this solution produced a make span of 576. And so this was the most optimal solution that we found. Machine 1 in this case is what is contributing to the make span. And machine 1 has a gap between job 4 and job 2. And so when I was evaluating the solution, I was curious to see what would happen if we swapped the job sequence on machine 1, basically to put job 3 where job 4 is, and job 4 where job 3 is. And when we look at that solution, we see a ripple effect, meaning that although machine 1's overall runtime was reduced, it caused machine 2's runtime to increase, which contributed to a larger make span. And so it's not always obvious when looking at a Gantt chart to see like, oh, we just need to switch these jobs and our overall make span will. There's when two operations are flipped in scheduling, there's a ripple effect, which changes the overall make span in ways that aren't super clear, easy to see. And so I touched briefly on these challenges in using Wisdom of Crowds and open shop scheduling. But just to formalize it, good schedules don't always look similar. So building consensus doesn't always help directly. And optimal solutions or close to optimal solutions and optimal solutions, they may not exactly look similar. And so they might not have obvious repeated structural patterns. And there's interactions between machine schedules and changing these machine schedules can cause ripple effects that change the runtimes of other machines. And so those aren't always obvious to see as well. So going over our basic genetic algorithm, how we did this. So we have a current population, and the current population, from the current population, we have a quarter of them are the expert class, so the top 25% performing schedules will move on to the new generation. And we have 3 Wisdom of Crowds crossover operations that I'll go over. And so that makes up 25, 25, 25, and 25. So replacing the current generation with the new generation. And the way that we started the genetic algorithm, our initial population, we simply created 100 random schedules, and we selected the 40 with the shortest make spans. And so that was our initial population, and 10 of those were our expert class. Right, and then originally for smaller open shop scheduling instances, we kept it to just population sizes of 40. We went ahead and doubled that for the larger instances, just to kind of give us some better results. And the stopping criteria also changed. For the smaller instances, we said 20 generations without improvement was our stop limit, and then 50 generations without improvement was our stop limit for larger instances. And then we maxed it at 100 generations and then 200 generations for the larger instances. And then another thing to point out is that we didn't use any mutations. We wanted to basically contribute all of our results to just Wisdom of Crowds. And so applying a mutation, we didn't think of a good way of using a mutation that was Wisdom of Crowd related. So we kept it to just 3 Wisdom of Crowd themed operations. And so in genetic algorithms, usually you have 2 parents, and the 2 parents produce an offspring, and that's it. The way that I think of our genetic algorithm using Wisdom of Crowds is that each offspring really has 10 parents, or in larger instances, 20 parents. But basically, an offspring's parents is the expert class. So you're actually pulling traits from all of the experts in one way or another. And so we have 3 crossover functions. So Wisdom of Crowd operations, Wisdom of Crowd sequences, and Wisdom of Crowd adjacencies. I'll go into detail what each of those do. But for each of them, when there was more consensus, it led to a higher probability that the traits that each crossover was examining passed to the offspring. And so I wanted to use probability-driven crossover functions. That way that the same algorithm applied to the expert classes would often lead to different offsprings. So it was unlikely that you'd have twins, be in the new generation, or less likely until we went to convergence. Right. So from operations, just putting it simply, the position that a job was on a machine sequence, if that, let's just do, for example, if job 1 was commonly the third job on machine 0 schedule, then it was more likely that it would be selected to be in that third slot in the next for the offspring. And so we're just basically matching position by position consensus. And so we built a probability matrix, and then we used the probability matrix to place each operation on a machine schedule. And then that often led to machine schedules going through the same operation twice. And so we had to have a repair function, basically clean those up. The second crossover function was sequences. And so this basically did the same thing as the prior crossover function. However, we just viewed, overall rows. So if a machine row was common among the expert class, then we just kept that whole entire machine schedule in place and only moved around the other machine schedules. And so we mixed and matched top performing machine schedules and then built consensus that way. And then the third crossover function using wisdom of crowds was adjacency. And so adjacency between two operations. And so this is the most similar to the traveling salesperson, where we can think of how common did one city go to the city A go to city B? How often did job A go to job B on a machine is sort of what we're thinking here. Right. And then for our test, we just tested 10 open shop scheduling instances, and then we compared it to a pure random search algorithm that was kind of set to a similar runtime as our genetic wisdom of crowd operation took. And so we had so we want to compare results there. Right. So here is a demo of what we did. And so just running the function, kind of skip ahead. This was for 10 jobs on 10 machines. And so it's going through, in this case, 200 generations, and it took about 20 seconds. And we see the Gantt chart that it produced. It doesn't look optimal, but all the machines sort of did have, similar runtime. So it's hard to say if there was anything better, but then we see the make span per generation that follows. And then this chart represents the performances by each wisdom of crowd crossover function. And so what we actually showed was that the operation that kept good machine schedules, individual machine schedules, performed a lot better. Okay, so as I said, the orange represents the machine schedules that transferred over, and that was consistently the best operator. So some conclusions that we made is that the genetic algorithm wisdom of crowd hybrid consistently matched or modestly outperformed the random sampling baseline. So that was true almost in all instances. Of the 3 crossover functions we had, the one that matched machine schedules was the best, and the wisdom of crowd adjacency was the weakest operator, and it barely improved. So basically the next future work would be to replace that. We didn't do anything that matched. We had a machine job sequence, but I was curious if job machine sequence, if that would contribute, if we did a consensus built on that, if that would increase. and then also compare it to something stronger than just pure algorithms, maybe an ant colony optimization, more traditional solutions to OSSP. And that's my project. Thank you for listening, and take care. Bye.